Hi, our topic for today is section 2.6, Euclidean algorithm. So what's our goal in that algorithm? To find GCD of two integers A and B, where GCD stands for greatest common divisor. So method repeated division, which is what quotient remainder theorem. So generally, I think the best way to understand this is to just do one example, and then from there to see what's happening, and then we'll just formulate the theorem and so on and so on. So in example 2.6.3, here's our goal. We want to find GCD of 4,500 and 6615. First, in order to understand the question, we need to understand what does the GCD mean. So K, so here's the definition, and then we'll go back to the example. So GCD of two numbers m and n is such a number, let me call it a D, such that, so I'm describing D, if and only if, as the name says, it's a common divisor. That means D divides m into m, D divides into n, and D is the greatest such number, such integer. Of course, one can complain that this is not too precise or too formal. What does it mean that D is the greatest such integer? That means if someone else does the same, that means for every E in Z, kind of like that's an integer, then if E satisfies the same properties, that means if E divides M and E divides N, then E is less than or equal to D. So all the other common divisors are less than or equal to our number. So in order to get the greatest common divisor, we will apply a Euclidean algorithm, and actually I will explain how the algorithm works while doing it, and then we'll formalize the statement. So here's the procedure. You divide the greater among them with the smaller one. So using quotient remainder theorem, says 6615 equals 1 times 4,500. You can use calculator for that. You divide, you get 1 point something. So you know that quotient is 1, then you subtract it, and you get oops, I did differently in my notes. Doesn't matter, then I have to calculate here. I didn't bring calculator here, but doesn't matter. 1 times 4,500, and then what is the remainder? So that would be 2115. Yes. All right. Now comes the crucial step, and that is to remember who are the important numbers and who are irrelevant numbers. So these are important numbers. Quotient is not important. Now what happens? Among the red numbers, this one disappears. Those two advance to the left. So you go like this. You take 4,500 equals you divide it by 2115, and you look at the remainder. So these are two red numbers. So it's 2 times 2115, which is what? 4,230. 4,230, so this is 270. And that's next to that number. And then you keep going until you reach a step where there is no remainder. So what you do, now 2115 goes to the left, equals 270 plus the remainder. So what would the remainder be? What would the quotient be here? Probably 4. 980, no, 4 times 270, yes, it's 1080, and what's left is, no, not 4, it's maybe 9, maybe 8. Too much. 7. I should have probably brought the calculator. So what would that be? 0, 9, 14, and 4 is 18. So 18 and 90. So this is 110 to 25. 18, 19 to 25. Again, the same procedure. Then take 270 equals 225, then it's 1 times 225 plus 45. Then you get 225 is what we divide by 45, and now the remainder is not there. Actually, it's divisible, and it's 5 times 45. And here we just stop. So that's the procedure. You stop when there is no remainder. And then what's your answer? The last non-zero remainder, which is 45. And then you say the following. So GCD of 4,566.15 is 45. If you look in my notes, actually I did it differently. I used factorization. And then from that factorization, comparing the factors, the way it's being done in algebra courses, then you can see there are common factors and common prime factors, and that will give you factorization. This is much better method. Why? Because I told you last time that prime factorization is a very complicated procedure, and generally you cannot expect to easily have prime factorization for huge numbers. This is a very simple procedure because it just involves division. So it uses much less memory and less power of mathematics than the other methods. So this is the real method to learn. So, and this is how it always works. So it's fairly simple to apply. Will it always work? Yes, and this procedure is unique. I gave you proof by induction in the notes, but generally you don't have to go by induction. Just common sense tells us what the quotient remainder can always be applied as long as you divide it by non-zero number. So as long as you get non-zero remainders when they are pushed to the left, you can divide by them and get unique quotient and the remainder. As long as it's not zero, you push to the left. And of course, if this is a decreasing line of numbers, because this is each remainder is smaller than the previous one, because that one was shifted to the left, then this is a decreasing line of numbers. So at the end, the procedure has to stop. That means at the end, you have to reach non-zero, you have to reach a zero remainder, and last non-zero remainder, that is a GCD. And then I want also, so I told you a few times that illustrations are not proof. So this is not proof of the theorem, this is just illustration of a procedure. But sometimes those illustrations give us a better idea of what's going on than formal proof. So that's why here in my lecture, even if that's not a proof, I'm trying to kind of illustrate it better what's happening. So the question is, why is this procedure always giving us a GCD? Why is this 45 a really common divisor of both those numbers? So generally, again, the proof can go by induction, but I can illustrate it here. Look at the last line. 225 equals 5 times 45. So 45 divides into 225. Now you go to the next line. 45 divides into itself and divides into 225. That's why it divides into 70, because it could be factored out from here and from here. So when you factor it out, so 45 now divides into 70 as well. And then you keep going up. Now if you go to this line, it divides into 225 because you already have that, and divides into 270. So 45 divides into 2115. Now you go on line up, it divides into 70 and 21. So you generally, whenever you kind of cover two of them, you cover the third one, then in the next line you get a new number and so on. So 45 from this line divides into 4500, and finally on this line 45 divides into 6615. So it divides in everybody along the way, but what we are interested in is top of the list, where our beginning numbers are. So it's 45 divides both of them. And then what? Then, so 45 is a really common divisor for both of them. Is it the greatest one? Yes, why? Because now you go the same thing but downwards. So you see, if someone divides both of them, then it needs to divide to 115. And you go next line, oh, now it divides those two, and so on. At the end, if it divides those two, it must divide 45, so it must be less than or equal to 45. And actually proof that is in the notes, just repeats the same idea. The only difference is, since it's not example, it has to go in general, it's done by induction on the number of lines. But I'm not going to repeat that one because I'm not going to ask you to provide that proof on your exam. And then I'd like here at this point to just do one more thing, and then we'll finish the section with that. And that is, there is something interesting and good for application and something that we'll use in the future. And that is, so see, I started with number 6615 and 4500, and I got number 45 at the end of the procedure. There is a theorem that says that actually 45, so, or problem statement that we'll need in chapter 6. I'm squeezing this here because I needed this all to call it statement. There are numbers U and V such that 45 equals 4500 times U plus 2115 times V, which is a strange statement because those numbers are huge and you can express this small number as their linear combination, but the statement is true. Generally, if you want to say this story anecdotally, that would be if you have two dishes, one of them with 4,500, let's say, gallons, and the other one with 2,115 gallons, you can measure 45 gallons using those two. And this is called Bézout's theorem. Bézout. It's not in my notes, later on in chapter 6. And how do you execute that? Generally the same way as a minute ago, but just going backwards. But it's very simple, but just you need to be careful and well organized. So go from the bottom, the same way as we made the proofs. So you express 45, so there is a line here, you see. The oldest ones, and here are the smallest numbers. So you go gradually and kind of occupy those bigger numbers step by step. So here it is. Here I'll express 45 using 270 and 125. That's very easy. 1 times 270 minus 1 times 225. Well, be careful here. Never to multiply those red numbers. Red numbers are like vectors, if you have linear algebra. That means you just use them as placeholders. Only those numbers could be changed, but 270 and 225 will never be multiplied out. Then what do? In your list, 225 is kind of younger than 270, smaller, showed up later, and this is what you do. You keep the older one, 1 times 270, and you trade 1 times another. You trade 225 according to the previous list. So what is 225 from this line here? It's 2115 minus 7 times 270. Okay. And I put those protected values in the box so that they are never. So I look at this as a polynomial. So if I get rid of parentheses, I have the following: 1 times 270 minus 2115 and plus 7 times 270. So I never multiply, but I can do this. 1 box and 7 boxes of the same type could be combined. So this is 8 times 270 minus 2115. And really, if you multiply out and subtract, you'll get your 45. That's it. Now I have again 2 members, a little higher level. So who's lower among them? 270. So I trade 270 from the line where 270 appears. So what would that be? It would be 8 times, instead of 270, I write 450. No, 4500 minus 2 times 115. 2115. Those are protected numbers, don't execute it, just outside coefficients could be multiplied. And minus 2115. Now what I distribute, 8 boxes. Minus 16 smaller boxes. And minus 1 more smaller box. So what would that be? 8 times 4500 minus 17 times 2115. Am I there yet? No, I'm here on those 2. Now the last step is to trade 2115 using 6615 and 4500. So from that line I trade the younger one. I'd like to keep it here so I don't go somewhere else. It's 8 times 4500 minus 17 times 2115 would be traded as 6615 protected minus 4500 protected. Now when you distribute and combine 4500s, you get plus 17 and 8 will be 25, so you get 25 times 4500 minus 17. Oops, this is probably not readable. Let me correct this. Is camera catching this? Maybe not. Repeat it up there. Math plus 25 minus 17 times 6615. I will repeat it on top. So here it is, 45 equals 45. Sorry, I said it wrongly. I went too low, 6615 should be here. The first given one. So those 6615. So what are those numbers? It's 4500 times 25. And plus, this V is negative, minus 17 times 6615. Here it is, those are U's and V's. As I said, this is sometimes useful for applications to express GCD as a combination of two starting numbers, but starting numbers here I wrote this wrongly. So I need 6615, and then we succeeded, as I said, that procedure goes backwards through Euclidean algorithm, but you have somehow to keep track of those protected numbers, so you never multiply, you treat them as x and y, combine alike terms, but never execute multiplication.